Hello everyone, so our group will be present about heat transfer. The heat conduction equation, a partial differential equation, explain how the distribution of a certain quantity or heat changes over time in a solid domain as it naturally flows from higher to lower concentration. If the temperature is a function of all three coordinates and the time, that is t equals to t, x, y, z and t. Here you can also see the equation of the 3D steady state with heat generation, the equation for 3D steady state without heat generation, and also the equation about Laplace equation. When a time derivative or a property change with respect to time are present in an equation, it is generally referred to as a steady state heat transfer equation. In contrast, when neither a time derivative nor a property change with respect to a time are present, the equation is referred to as an unsteady state heat transfer equation of conduction. The main goal of this project is to use MATLAB to iteratively solve the transient 2D heat conduction equation using Jacobi, Gauss-Seidel, and successful over-relaxation for both implicit and explicit schemes. So this is the problem statement. Computation area is square. The boundary conditions are left is equals to 400 Kelvin, right is equals to 600 Kelvin, top 800 Kelvin, bottom 900 Kelvin, and the initial temperature is 300 Kelvin. And this is the flowchart. We have the inputs, the process, and the output.
How to solve the transient 2D heat conduction equation by using iterative solver with Jacobi method. Firstly, we have to input the parameters, number of grid points in x, and x is equal to 10, and number of grid points in y, and y is equal to 10, and t equal to 1000, number of time steps. Next method to create the grid points in x. X is equal to linspace 0, 1, and x. Y equal to linspace 0, 1, and y. This is the method to create the grid points in y. This is dx, is the step size for spatial x chord, and dy, the step size for spatial y chord. Now we have to define the absolute error criteria. Error equal to 9 exponent 9 is reinitializing the error, and the tolerance is equal to 1 exponent negative 4. dt time step is equal to 1 exponent negative 3. Here is defining the boundary condition. T underscore L is 400, T underscore R is 800, T underscore T 600, and T underscore B is 900. This one is left side of the domain should be at 400K. This one is the right side of the domain should be at 800K, and T underscore T is the top side of the domain should be at 600K, and T underscore B 900 is the bottom side of the domain should be at 900K. This here is to define the initial condition, and after we define the initial condition, we have to assign the T value at the corner, and then keeping the backup of T as T underscore initial equal to T and T underscore all equal to T. So now this is the calculation of 2D transient heat conduction equation by Jacobi method. The Ct equal to 1 here is the counter variable to show starting iteration so that it updates its value every time for the loop when it's executing. Ji equal to 1 here is the number of iteration by 1. Now we start our loop. This here, while error is more than tolerance, is the while loop. The while loop will run until the error is more than the tolerance value. And here, the for loop is to run for x values from 2 to the last node minus 1. This is the for loop that runs for y values from 2 to the last node minus 1. Okay, we assign the terms here. Term 1, term 2, and term 3. And this is the equation. Okay, this error is to calculate error to decide whether while loop should stop or not. This here is to update the temperature array for the next iteration. This Ji, as I mentioned before, is the iteration. It is used to incrementing the iterations by 1. And t underscore initial equal to t. Okay, this is the code for plotting the values of t. X label here, x-axis, y label, y-axis. The pause here is the pause command that slow down the animation at these seconds. MCT get frame GCF. For this one is for each iteration. For loop, the counter static value get updated with addition of 1. This video file is to generate video file that consists the file name. This one is to open the video file. Write video is to write captured frame in the video, and close video file. When we run this program,
Hello, my name is Belvena Sonia Benjamin, and now I'm going to present the MATLAB coding for solving steady and transient second dimension heat conduction equation by using Gauss-Seidel method. And the first step we need to do is to key in the input parameters, where nx here refers to the number of grid points in x, and ny refers to the number of grid points in y. And both these I will key in the value, which is 100. And then we need to create the grid points in x and y. So, to create them, we will use linspace. One and x. And same goes to y. We will also use linspace. So this equation here is the derivation, and after that we need to define absolute error criteria. And the error here I will input the value E9, and as for the tolerance, I will input the value, and the next step we need to do is to define the boundary condition. Firstly, TL. TL here refers to left side of domain, and it should be at 400 Kelvin. Next is TR. TR is the right side of domain, and it should be 800 Kelvin. Next is TT. TT here refers to the top side of domain, and it should be 600 Kelvin. Next is TB, which is the bottom side, and it should be 900 Kelvin. Next is to define the initial condition, and here you can see I already typed this coding earlier. I just put in the value here. And the next step is we need to assign the t-value at corner, and here I also have typed the coding earlier, and we need to key in one by one the values that provided. And then we need to keep the backup of t, and here are the two coding. We need to keep the backup. And next, we need to calculate the second dimension steady-state heat conduction equation by using Gauss-Seidel method. And you can see the coding here. I have key in the value one by one and I use the if, while and for while loops one by one. And last but not least, we need to plot the value of t into the graph. So the coding is like this. And when we run this coding, a figure will be displayed, and this is the result. This is the GUI output for the coding that I have just made just now. That's all from me. Thank you.
Hello, my name is Valerie Olga and now I'm going to present steady and transient 2D heat conduction equation by successive over relaxation method. The first step is we need to input the parameter. For the nx is the number of grid point in nx and ny is number of grid points in ny, and both I'm gonna key in same number, which is 10. After that, we need to create the grid points in x and y, and here we use linspace, and the below is the derivation. After that, we need to create the grid points in x and y. We use linspace, and then the below is the equation for derivation. Next, we need to define the boundary condition. For the first one is TL, and TL refers the side of domain and it should be at 400K. TR, which is side of the domain, right side of the domain, and should be at 800 Kelvin. And the TT is the top side of the domain and should be at 600 and TB at 900. Next, we need to define the initial condition. As you can see, I've already typed in the coding. Now we have to assign the T value at the corner, and we can see here in the screen. And we need to key in one by one. Next, we need to keeping the backup of T for the T initial, T all, and T end is all equal to T. Now we will do a calculation of 2D transient heat conduction equation by SOR method. The CT here is CT equal 1 is a counter variable and GS equal to 1. Here we will use for loop and while loop. Now we will start the coding. For the while loop, error must be more than tolerance, and the looping will continue if the error is more than tolerance. Next is the code for plotting the value of t. For the axis label, x label is x-axis and y label is y-axis. And the pause here is pause command to slow down the animation at this second. The video file here is to generate the video file that consists of file name. And lastly, close is to close a video file. After all the coding complete, we need to compile it to see if there is an error. If there is no error, and then we will run this program. And this is the output, and this is the graph of number of SOR implicit. That is all for SOR method.
For the conclusion, from above table, we can conclude that Jacobi is more than Gauss-Seidel, is more than successive over relaxation according to the number of iterations computed for all methods and schemes. It can also be concluded that steady state is more successful as it takes less computational time because it do not have any time derivative term in it, and along with less number of iterations. In case if we talk about explicit or implicit, The explicit is more effective as it takes the least number of iterations in order to provide the accurate result. SOR or successive over-relaxation is more effective iteration as it consumes less time and iteration whether we talk about explicit or implicit. Thank you for watching.